Summary of the nature of roots. Hello everyone. Before we dive into today's lesson, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored the power of the discriminant, that specific part of the quadratic formula, and learned how it allows us to predict the types of solutions a quadratic equation will have, all without the need to actually go through the long process of solving the entire equation. Today, we are going to bring all of that knowledge together. This section serves as a comprehensive summary. I will provide you with a systematic, step-by-step approach to determining the nature of the roots for any quadratic equation, provided it is in the standard form of a x squared plus bx plus c equals 0, where it is not equal to 0. By the end of this session, you should feel confident in identifying exactly what kind of solutions to expect just by looking at the coefficients of your equation. The discriminant formula. Now that we have introduced the purpose of our summary, let's look at the specific tool we use to make these predictions. To determine the nature of the roots, we don't need to solve the entire quadratic equation. Instead, we focus on a single value called the discriminant, which we denote with the capital letter D. The formula for the discriminant is b squared minus 4ac. By calculating this specific value, we can move straight into identifying which of the three possible cases we are dealing with. Summary of the three possible cases. Now that we have identified the formula for the discriminant, let's look at what these values actually tell us. Depending on the value of D, the roots of our quadratic equation will fall into one of three specific categories. First, let's look at case 1, two distinct real roots. If the discriminant is greater than 0, the quadratic equation has two different or distinct real roots. Mathematically, this means that b squared minus 4ac is greater than 0. In this scenario, if you were to graph the equation, you would see the parabola crossing the x-axis at two separate points. Next, we have case 2, two equal real roots. This happens if the discriminant is exactly equal to 0. In this case, the two roots are identical, which is why we often refer to this as a repeated root or even a single root. Mathematically, we express this as b squared minus 4ac equals 0. Here, the vertex of your parabola just touches the x-axis at one single point. Finally, we have case 3, no real roots. If the discriminant is less than 0, the equation has no real roots. This occurs because, as you might remember from our study of square roots, the square root of a negative number is not a real number. Mathematically, we write this as b squared minus 4ac is less than 0. In this situation, the parabola stays entirely above or entirely below the x-axis, never touching it at all. In the next slide, I will show you a systematic, step-by-step guide on how to apply these cases to any equation you encounter. Step-by-step guide to determine the nature of roots. Now that we have reviewed the three possible cases for the discriminant, let's put this theory into practice. I want to give you a clear, systematic approach so that you can approach any quadratic equation with confidence. To find the nature of the roots for any given quadratic equation, you should follow these 4 essential steps. Step 1. Arrange the equation in standard form. Before you do anything else, look at your equation and ensure it is written in the form at x squared plus bx plus c equals 0. If you see any terms sitting on the right side of the equals sign, move them over to the left side by performing the opposite operation. This is crucial because if the equation isn't set to 0, your values for a, b, and c will be incorrect. Step 2. Identify the coefficients. Once your equation is in standard form, carefully pick out the values for a, which is the coefficient of x squared, b, which is the coefficient of x, and c, which is your constant term. I must emphasize, be very mindful of the signs. If a term is being subtracted, that negative sign belongs to the coefficient. Step 3. Substitute into the discriminant formula. Now, take those values you just identified and plug them into our formula for the discriminant, which is d equals b squared minus 4ac. Just be careful with your arithmetic here, especially when squaring negative numbers. Finally, step 4, analyze the result. Once you have calculated the numerical value of d, compare it to 0. Is it greater than 0, equal to 0, or less than 0? This comparison will tell you whether the roots are distinct, equal, or simply do not exist in the real number system. To show you how these steps work in a practical, real-world scenario, let's look at the next slide involving an engineering problem. Real-world application example. Imagine a scenario where a civil engineer is tasked with designing a rectangular garden. The project has two strict constraints. The perimeter must be exactly 20 meters, and the desired area is 26 square meters. The engineer's first challenge is to determine if such a garden is even mathematically possible to construct. Let's walk through the step-by-step solution together. First, we need to formulate the equation. We'll start by letting L represent the length and W represent the width. We know the formula for perimeter, P, is 2 times the quantity L plus W, which equals 20. If we divide both sides by 2, we get L plus W equals 10. From this, we can express the width in terms of length, so W equals 10 minus L. Next, we use the area formula, where area, A, equals L times W, which must equal 26. By substituting our expression for width into this equation, we get L times the quantity 10 minus L equals 26. Distributing the L gives us 10L minus L squared equals 26. Now, following the important step we discussed in the previous slides, we must rearrange this into standard form. By moving all terms to one side, we arrive at L squared minus 10L plus 26 equals 0. Second, we identify the coefficients. Looking at our standard form equation, we can clearly see that A equals 1, B equals negative 10, and C equals 26. Third, we calculate the discriminant. We'll use our formula, D equals B squared minus for a C. Plugging in our values, we get negative 10 squared, minus 4 times 1 times 26. Calculating this, 10 squared gives us 100, and 4 times 1 times 26 gives us 104. So, 100 minus 104 leaves us with a discriminant, D, of negative 4. Finally, we reach our conclusion. Since our calculated D is negative 4, which is clearly less than 0, we fall into case 3. There are no real roots. In a real-world context, this tells the engineer that it is physically impossible to build a rectangular garden that meets both of these specific requirements. Now that we have reviewed the theory and the 3 possible cases for the discriminant, let's put everything we've learned into practice with a real-world application. As we move to the next slide, I want you to pay close attention because I'll be highlighting some common pitfalls that could lead you to the wrong conclusion in problems like this one. Common mistakes to avoid. Now, before we wrap up our summary, I want to pause and discuss some common pitfalls. Even if you understand the theory of the discriminant, it is very easy to make small computational errors that lead to the wrong conclusion. First, let's talk about sign errors. This is perhaps the most frequent mistake I see. When you are identifying your coefficients, you must include the sign attached to the number. For example, if you are looking at the equation x squared minus 5x plus 6 equals 0, the value of b is negative 5, not positive 5. Forgetting that negative sign will completely change your calculation for the discriminant. Second, be very careful when squaring negative numbers. When you are calculating b squared in our formula, remember that the square of any real number, whether it is positive or negative, is always non-negative. A common slip-up is to say that negative 5 squared is negative 25, but that is incorrect. Negative 5 squared is actually positive 25. Always ensure your b squared term is positive before you proceed to the subtraction step. Finally, always double-check your standard form. As we saw in our step-by-step guide and in our engineering example earlier, you cannot accurately identify a b and c until the equation is set to 0. Students often try to calculate the discriminant while there are still terms on the right side of the equals sign. Always move everything to the left side first so that the equation is in the form x squared plus bx plus c equals 0. If you get this step right, the rest of your calculation will be much more reliable. Key takeaways. First and foremost, remember that the discriminant, which we denote as d, where d equals b squared minus 4ac, is your primary mathematical tool for determining the nature of the roots without needing to solve the entire equation. To recap the 3 specific cases we discussed earlier, if the discriminant is greater than 0, you will have 2 distinct real roots. If the discriminant equals 0, you are looking at 2 equal real roots, or what we sometimes call a repeated root. And, as we saw in our engineering example, if the discriminant is less than 0, there are no real roots to be found. Finally, keep in mind that this isn't just an abstract classroom exercise. The discriminant is an essential concept used in the real world, particularly in fields like physics and engineering, to check the feasibility of constraints, helping professionals determine if a design or a physical scenario is even mathematically possible before they begin construction. All right, we have reached the end of our lesson, so let's bring everything together with our key takeaways. That concludes our summary. Great job staying focused throughout the lesson.